Okay, I guess we can get started. We don't have everyone in, but some people come in around 1. So you got, did everybody get feedback on milestone presentations? You got my feedback during the talk, so hopefully you remember that. But if you don't remember that, everything is recorded, so you can go back and get that. Please address that for the next milestone, actually for the project. We'll see if we'll do a similar thing for the next milestone. But we may actually, we'll definitely do a poster session or a similar presentation for the project. And you've gotten the feedback through email as well, hopefully. Everybody? Okay, that's good. Yeah, please address that as well. That's, any questions, any thoughts on the milestone session? Some of you stayed for other people's presentations, so was that interesting? That gives you a good idea of what other people in the class are actually doing too. So if you haven't actually stayed, we have the benefit of seeing the presentations online, so you can take a look at everyone else's presentations, because it's a good variety of topics that are being researched. And I think one of the good things you can learn in this class is by looking at what other people are doing and what kind of topics are being researched within the course, because there's a good variety of topics spanning systems, actually, what you guys are doing, for example, systems architecture boundary, as well as the lower boundary, almost circuits architecture boundary too. So hopefully that should be interesting. But please address the feedback for the next part of your project. We'll probably ask you similar questions if you haven't addressed it. Okay. In the meantime, we've covered a lot of topics also, so I'd like to discuss some of these things, and I'd like to take your questions, certainly. So the last recitation we had was actually the exam solutions, and then we had the milestone sessions. And today we're going to talk about basically whatever questions you have on the lectures. So we've covered quite a few topics. Some of it is actually review for people who've taken 447, and that's how it's supposed to be, actually. So since the exam, let me just brush up your memory a little bit. Since the exam, we've covered memory interference and quality of service. These are memory controller designs that provide better quality of service, better fairness, reducing interference in different ways. We've covered dumb resources, as you remember, source throttling, memory channel partitioning, different approaches. Actually, today people are looking into more finer grain partitioning, like bank partitioning between different threads, such that you get better performance. Remember, the memory channel partitioning paper partitioned the applications to different channels such that you minimize interference. Do you guys remember that? It's been a while, I know. It's 10:28. Right now we're at 11. What is today? 13, yes. But it's good to think about these things because well, we may ask you questions on these also. And they're also important topics. So people are actually thinking about partitioning at the bank level also, instead of at the channel level. So you put the data of different applications to different banks. What are the trade-offs there? Like what, is there a benefit to doing bank level partitioning compared to channel level partitioning? You guys remember? Say it again? I guess, yeah, if you don't have channels, that's right. For going finer grain, bank level partitioning is a finer grain method. And that enables reduction of interference better, certainly. Especially if you have a single channel, you cannot partition across multiple channels, obviously, right? So bank level partitioning arguably is well, it is a finer grain method, but it can give you better interference reduction because you're at a finer grain. Yeah. Say it again?
You need more pins for more channels.
More bins?
Pins.
Pins, yes, that's right. For more, if you want more channels, you need more pins. But if you already have more channels, you can partition them across different applications. But this finer grain partitioning enables you to have more control, right? If you have 2 channels, you have only 2 choices to allocate a page for an application. Basically allocate in a preferred way for an application. Whereas each channel may have, let's say, 8 banks and 2 ranks, or 2 ranks and 8 banks per rank. So that's 16 banks. Right? And if you have 2 channels, that's 32 banks. Now you have 32 banks to partition. Okay?
So
Yes?
if you do like a bank partition, you can exploit DLP and level parallelism.
Y-
The channel, you probably can't.
How so?
So I don't know, since the bank, since you partition on band is a finer granularity,
Mhm.
like you can do more lower level.
That's right. So I think what you're saying is basically you could allocate 2 banks for you could allocate 2 preferred banks for an application from different channels, right? That way you can now exploit that channel level parallelism, right? Whereas in the channel partitioning that we've discussed in class, you allocate a preferred channel for an application. Maybe you get data from different banks, but you cannot exploit channel level parallelism in that case. So you get better channel level parallelism if you do bank partitioning, so you have more control. That's right. Any other thoughts? So these are actually topics that are being researched right now. How do you best reduce interference between different applications? And partitioning is one of the good approaches because it can really eliminate interference, right, between 2 applications. If you allocate 2 applications to different channels, you really eliminated that interference. And that's actually one downside of potentially bank partitioning in a single channel. If you partition the banks in a single channel between different applications, you haven't completely eliminated the interference, right? Because those banks actually share the bus. You've reduced the interference, but not completely eliminated it. Those banks share the command bus, data bus, and address bus. I guess, can you do better? You could potentially take into account both, right? You could allocate a preferred channel and maybe also allocate preferred banks for an application. So you can design a mechanism that takes into account both channels as well as banks to do better than both channel level partitioning and bank level partitioning. That's something I have not seen yet, but that could be interesting. I think going forward, taking into account the entire DRAM structure, or main memory structure, I should say, to minimize interference, is better than just looking at channel partitioning or bank partitioning alone. Does that make sense?
Can you do like row level or page level? It's like
Oh.
more than that.
So yeah, page level, you already partitioned at the page level, right? Because 2 applications, unless they're sharing a page, they really allocate different pages. So that's already there. Lower level, lower than banks. Actually, that's a good question. We've covered the concept of subarrays, right? Subarray is smaller than a bank. And that gives you another freedom, right? That's the next level in the hierarchy. And maybe you partition subarrays across applications. Right? Of course, this works if you can somehow exploit subarray-level parallelism. You guys remember the idea of subarray-level parallelism? Coming out of your storage and getting into the cache now? Yes? No? Yeah. So the idea was, let's try to go over it very quickly. But this is what we covered in one of the earlier DRAM lectures, right? If you look at a bank, the bank is really not a monolithic structure. Remember, we've been drawing this picture. Bank, 2-dimensional array of cells, and then the row buffer, and then you have the row decoder over here. I'm not going to draw, and then the column decoder. Actually, maybe I'll draw that. This is the row decoder, and this is the column decoder, column mux, right? This was our bank for a while. But this is really an abstraction. Even this is an abstraction in today's systems. This bank, let's say this is 32,000 rows you have. And this is a 2-dimensional array of DRAM cells, right? This bank is harder to build. If you have 32,000 rows, the bit line that spans the entire cell becomes really long. So it becomes very high latency to actually design this bank with a huge long bit line. Does that make sense? Well, you remember the DRAM cell structure, right? You have a capacitor and a transistor. Basically, this is connected to the bit line. Remember, and you have 32,000 of these hanging off the bit line. Imagine 32,000 of these. This bit line capacitance becomes huge with all of these components connected to it. As a result, the latency is large. Actually, that latency will be much larger than what we have today. So because of this, because we don't want this huge latency, what people do when they design any kind of memory, actually, well, in particular DRAM, they break this 32K into smaller chunks. And that's the idea of subarrays. And if you remember, we've covered this in the Subarray-level parallelism paper in ISCA 2012, briefly. But the idea is basically, instead of having this huge structure, you have smaller subarrays. Each of them have their own row buffers. This is subarray 0, let's say. And then you have another one, subarray 1. ... And let's assume that each subarray has 512 cells per bit line. So you still have these bit lines over here. Now you have 64 subarrays within a bank, right? Assuming this is 32K. Right. Now what we've done is we've reduced the latency to sense a cell, right? Because you have these sense amplifiers. And the latency to sense a cell is much smaller because the bit line is much shorter, right? So when you sense a row now, the row gets brought into these sense amplifiers. And you have many of these sense amplifiers, actually. We've broken the abstraction. The abstraction is that you really have a single row buffer, but really you have many row buffers in DRAM, in a DRAM bank. But today, what happens is only one of them can be enabled. So that's why the abstraction works. The abstraction works because when you access a DRAM bank, only one of the row buffers can be enabled, because you access only one subarray, and the data gets brought down into the subarray, and it stays in the row buffer. So you may ask, actually, how do you read the data out of these row buffers? Basically, what happens is you have what's called the global bit lines that are much at a higher metal layer. You have these global bit lines, I'll draw them like this, that run across subarrays. And that's how the data gets read out of the DRAM chip. And you can look at the Subarray-level parallelism paper for a longer description. Are you guys familiar with this? Some of you, yes. Some of you, maybe. OK. So that's the idea of subarrays. Today, these subarrays are not independent, because what happens is when you get a row address, it gets decoded, and then it gets latched. Basically, row address gets latched over here, decoded row address gets latched. And you have only one row address, one latch controlling all of the subarrays, which means that only one subarray can be enabled, right? Only one row in a subarray can be enabled. And let's say it maps to subarray 0. Then you enable this row buffer. So this row buffer is open. And then when you do a read, what happens is the data from this row buffer is read and sent through these global bit lines to the I/O circuitry out of the DRAM chip. OK? In a sense, today, the Subarray-level parallelism is not exploited. But what you can do is you can actually have what we discussed in the Subarray-level parallelism paper is, instead of having a single latch for all subarrays, you actually have separate latches, right? Let me try to draw this somewhere here. Actually, we have figures in your PowerPoint presentation slide, so you can take a look at them later. This is subarray 0, subarray 1, and I think you can still see it. So you have the row decoder, and you can actually have the subarray address latch, right? Now you can have multiple addresses latched and controlling different subarrays. So when you latch an address here, you can enable one word line here, which gets latched, which gets activated into this row buffer. When you latch another address here that goes to a different subarray, you can enable another word line here. Make sense? In the next cycle, for example. It's just like banks. Except banks have totally independent decoders, right? Here we're thinking of having a single decoder, but latching the decoded address in the subarrays. Okay? Now this enables parallelism within the subarrays, right? Okay? And you may think of partitioning data of different applications to different subarrays. And this gives you even finer grain partitioning capability, right? Because within a single bank, I showed you here, you have 64 subarrays, right? So now you have even finer granularity partitioning. 64 subarrays, let's say 8 banks, and let's say 2 ranks per channel, 8 banks per rank, 64 subarrays per bank, and maybe let's say 4 channels total. That gives you 64, well, you multiply all of these, right? What is the multiplication of this? 64 times 64, right? 4,096 different subarrays. And if you have, let's say, 32 applications sharing it, now you can actually think of these applications spreading their data in totally different subarrays. But it's really a hierarchy, right? The level of interference increases as you go deeper down into the hierarchy. 2 subarrays have more interference than 2 channels, obviously, because channels are completely independent, but subarrays are dependent on each other, actually, slightly. Right? If you remember from the subarray-level parallelism paper, you need to pipeline accesses. There's a subarray switching penalty. Because one subarray, if you read from this subarray, you can keep multiple row buffers active, but when you're reading from a subarray, you need to switch to that subarray. You need to enable that subarray. Because why? Why? Because these actually share these global bit lines, as I said earlier, right? You need to control which subarray actually drives these global bit lines. That's why you need to switch to that subarray. And that's a switching penalty. So if 2 applications actually are allocated to different subarrays, and if you're accessing their data concurrently, well, one of them needs to wait for a while for that switching penalty. So there is still interference. There's more interference in the subarray level. In the bank level, well, this will be your bank level almost, right? Between 2 different banks, there's still interference because they share the command data address buses. They don't share the global bit lines like we do here, but they do share the command data and address buses. And across the channel level, in the rank level, again, the buses are shared. Excuse me. Yeah, in the rank level, buses are shared also, but again, there's a rank switching penalty in that case. At the channel level, nothing is shared. So if you'd like to really isolate applications from each other, you'd better do channel partitioning. If you're OK with some interference between applications, maybe subarray level partitioning is good. Right? So I think this is actually an interesting topic to look into. But now you can make the trade-offs based on what you've learned, right, in this class. Any questions, thoughts? Maybe you can brush up by looking at the subarray-level parallelism slides on paper. Right. OK. OK, let's, I guess, go back this way. So yes, we've covered, this is one example of the dumb resources approach, right? The sources are not intelligent. The resources are not intelligent. You don't necessarily change the memory scheduler in this case, but you change the data mapping to reduce interference. Another approach is source throttling. Right? You throttle the applications that are very intensive, for example, and causing interference to others. OK, I guess let's move on. I'll just give you an overview of what we've done since the exam. Interconnects, like we've had 2 lectures on interconnects actually. One of them was a guest lecture by Papa Michael. Any questions on this? It's another important area actually, both on-chip and off-chip. How do you enable the communication substrate? And we've covered a lot of things, including topology, especially in the first lecture, router design, quality of service, especially in the second lecture. How do you minimize the interference between applications? Hopefully this is coming also. OK, any questions on that? No? And you've done some reviews. You reviewed the Ergia paper, for example. That's actually another concept that's important. That's the concept of slack, right? Which packets or which requests are more critical than the others. In that paper, the idea of that slack, how much can you delay a request before it actually affects performance, is used to do intelligent routing or intelligent prioritization within the on-chip interconnect. You could think of potentially similar mechanisms for the memory controller. Which request can you delay while having minimal impact on performance, right? Or while having no impact on performance? Associating this slack value with requests in the memory system is usually a good idea. The question is, how do you do it? Right? There was a mechanism in that Ergia paper. It's not perfect, but it's a predictor of how much slack you have. And that slack was not exact, right? The paper didn't really exactly say, this packet can be delayed by 371 cycles. Right? It'd be great if you can actually have that kind of accurate prediction, but that's very tough to do. It basically said this packet likely has more slack than the other one because it's going to travel fewer hops. And there's another packet outstanding that's going to travel much longer. Right? That means that I have some amount of slack. And that slack was expressed as a priority level. Usually, if you want to implement something, you don't have the full timestamps. You quantize some value to a priority level. And in that paper, it was prioritized to a priority level. And that priority level was used to prioritize between different packets at a router. The router looks at the priority level and says, oh, this packet seems to have more slack. Now let me prioritize that. Let me prioritize the other packet that doesn't have slack. Because if I delay the packet that doesn't have slack, it's likely that it's going to impact performance. Make sense? It's a cool idea, right? It's actually a good idea for resource management in general, I think. If you can associate that value, determine that value for everything. Threads, for example. An application, actually, if you go back and think about bottleneck identification and scheduling. We've looked at this parallel execution between barriers, right? You launch a number of threads in the beginning of the parallel section. Oh, yes, thank you. There you go. You launch a number of threads at the beginning of the parallel section, and one of them happens to execute for much longer, right? That means that all of the other threads actually have slack. We can maybe deschedule them even for a while and, I don't know, save power for that time. Right? So that's the idea. This is the idea of slack. This is the slack of this thread. This is the slack of this thread. If you can predict that thread, if you can predict that slack, you can do much better thread scheduling. Okay? So a lot of the concepts that we cover actually have very similar characteristics. You just need to kind of abstract them at a higher level and look at them that way. Also, slack depends on what you're trying to optimize as well, right? In this case, it's performance. But for example, you're designing a operating system for a cell phone. Your slack is how much your slack is probably dependent on how much you annoy the user, right? If the user gets affected by something, then that's probably a big problem. And everything else can be defined the slack of every other program, for example, can be defined based on whether or not the user will get annoyed. So if you can do that prediction, if you can design that system, you can design a much better system, probably. OK. So that was one thing about the interconnects. By the way, I hope you guys are doing the readings. Is that coming along well? I know there are a lot, but that's the purpose of this course. I mean, this is a graduate level course. It's to initiate you into both the fundamentals and recent research. And readings are an important part of this course. Are people OK with the readings? Yeah? Reviews? OK. Keep doing them. And I know you may laugh at me. There are a lot of other readings over here. But do readings beyond your review readings. That will enable you to do better research in the future and design better systems in the future. Because it's really, these readings, the readings you do are really, they may not look immediately useful, but they're really preparing you for something in the future. Because you may find a problem that you're trying to solve in the future, and you may think of one of these readings and say, oh, I had read something in computer architecture at some point in time, and maybe my solution can benefit from what they've done in that. Slack, for example, I think is a good one. That's, even though it's in a very specific context, it's really, the notion of Slack can be applied to different contexts. So that's why it's good to read them carefully. And you can certainly read the mentioned readings too. This, for example, is a very instructive reading. This connection machine technical summary. Maybe long, but you'll learn a lot. OK, let's see. Oh, yeah, these are the required readings for the interconnects. I guess this is GPUs and SIMD. OK. And then last week, I guess we've covered different execution models in a slightly different order. Yes?
So I had a question. Wasn't there like a guest lecture, I think on like the 28th of October, something like that?
20. Oh, is that Michael's lecture? Or?
No, that might have been the self-sharing.
No, that was.
Oh, is that Wenmei's seminar?
That doesn't sound familiar, so yeah, that's probably it.
OK, so that's actually not a guest lecture. That was a calcium seminar. But we should actually put it up online.
It's probably under the calcium section.
OK, yeah, that was a calcium seminar. That's why we didn't put up. So you can certainly take a look. Actually, we should put it up as part of the GPU lecture, because it was actually about GPUs. But you're not really required to know that material. It's more for research. Maybe it was incorrectly labeled as guest lecture, but it's not a guest lecture. It was a calcium seminar. It was still interesting, so I encourage you to look at it. That was the one you're thinking of, right?
I think so. I
Because-
remember I got an email
Yeah.
on like the 28th.
Yeah, that was more, that should have been calcium seminar, not guest lecture. But it was here, you're right, it was on the 28th. Yeah, it was actually on programming of these heterogeneous architectures, like GPU architectures. But it is an important topic also. So you might want to take a look at it. Because GPUs are actually important drivers of computing today. They're not necessarily general purpose at this point, but people are trying to make them execute many, many more applications than they're capable of today. And we've covered those. Basically, this past week, we've covered, in a sense, different execution models, right? We've started with Flynn's classification of computers. You remember that? Based on the instructions and data, you have 4 different types of computers: SysD, SIMD, MISD, MIMD. And we covered actually pretty much everything in that space. We focused on SIMD to begin with. And GPUs are an example of SIMD engines with one key difference, right? It's not really hard-coded SIMD, I should say. The programming model is not SIMD. The programming model is really thread-based programming model. You write a thread, and many threads do the same thing, right? And those threads actually have independent contexts of execution, but when they execute the same instruction, they don't need to decode the instructions separately, right? It's really SIMD. SIMD, actually, you have single instruction, multiple data. In GPUs, you can actually dynamically determine which threads execute the same instruction, right? And amortize the overhead of executing that instruction by exploiting the hardware that's essentially SIMD-like hardware, right? It's basically very similar to vector and array processors, except the flexibility is in that programming and the support that's required to support that programming. Yes?
I didn't understand the distinction between vector and array processors.
Oh, OK. That's good. Let's see. I should have it somewhere. Oh, no. See, this is bad design. If you don't put the full name of a file, and if the files have similar names, how do I pick the right one? Try 3, this one? No, that didn't work, right? There you go. Yeah, bad design. This is part 3, so that won't work. Maybe we'll go back part 2 and part 1. OK. Has to be there. OK, there you go. Can you see? So basically, they're both single instruction, multiple data. A single instruction operates on multiple data elements. The major difference, the only difference, this is actually, let me get back up. In the lecture, I said this, but this is a very strict definition. Today, most processors are both vector and array processors. For GPUs, for example, both a vector processor and an array processor at the same time. But in the strict sense, in the pure sense of the term, in array processor, a single instruction operates on multiple data elements concurrently at the same time. In the vector processor, in the strict sense of the word, a single instruction operates on the different data elements in consecutive cycles at different times. Still, that single instruction operates on multiple data elements, but does that multiple operations happen at the same time or over time? That's the only difference. Does that make sense?
Well, you could have an array processor that's pipelining.
Yes, so now you're becoming array plus vector processor, right? That's pipeline. So pipelining is at a different level, right? I guess if you do pipelining, you're basically operating on. So when you say pipelining, I guess what you're saying, you have a load instruction that's operating on multiple elements at the same time, and later elements of the vector are operated on in the next cycle, right? Yeah. And then later elements are operated in the next cycle. Later elements operate in the next cycle. Now that's basically a vector processor and array processor together. You're using both concepts basically. That's why I said this is in the purest sense of the term. Does that make sense? So if you actually don't have pipelining, so this is basically the distinction, right? This is the array processor, and you're supposed to operate on 4 elements. With this load, you're operating on them at the same time, right? And that's it. And then the add comes, and then the multiply comes, and then the store comes. And then you're done. With a vector processor, the first element of the vector is operated on in the first cycle. The second element of the vector is loaded in the next cycle. The third element in the next cycle. The fourth element in the next cycle. Right? That's the main distinction. And you're absolutely right. If you want to have more elements, you can actually, instead of adding more processing elements, you can start pipelining the elements. Now you have a combined array vector processor. That's why this is a very strict, purist distinction. And most processors today, most SIMD processors today are a combination of both.
So this no longer looks like a SIMD.
They're both SIMD. Because SIMD means single instruction operates on multiple data elements. That's it. Right?
And that's what's happening here. A single instruction load operating on multiple data elements. In the vector also. You specify a single instruction load. It operates on multiple data elements, except it's in time. It's over time. Right? This is within space. Across space, you operate on multiple data elements. This is across time, you operate on multiple data elements. OK? That's the main distinction, space versus time distinction. And you're absolutely right. In today's GPUs, or actually many SIMD processors, it's a combination of both. What happens is you may have, let's say, 2 load units. Load 0 goes here, load 1 goes here. In the next cycle, load 2 goes here, load 3 goes here. And it's still the same instruction. You don't keep decoding it. This is actually, I shouldn't call it load 0, load 1. It's really the same instruction operating on different data elements. Right. OK?
It doesn't start looking like a systolic process,
The vector.
should use pumping data.
Oh, that's a good question. So that's why I think I had a food for thought in one of the slides says, what's the difference between systolic array and SIMD? Right? They're actually kind of similar, right? You're basically pumping data into a vector unit from the registers. And if you do chaining, you're actually pumping that data to another unit, perhaps, right? Remember, we covered chaining, vector chaining. So at some level, they're actually similar. What's the major difference? Yes?
Maybe the topology where you have a 2D, like top bottom.
That's right. So a systolic array is usually much more specialized. This is also specialized, but a systolic array is even more specialized. I'm not sure if you're reading this Why Systolic Array Architectures paper. Did we already read that? Or is this time? Yes. If you look at that, it's very, very specialized, right? It's specialized for a function purpose, whereas this can be more general purpose. This has instructions, load, store, add, multiply. That's the major difference. But you could think of this as a more general purpose, less specialized systolic array. Right? But this is some food for thought for you. But you're pumping data from the vector registers into the load units, and then the load unit is pumping data to the add unit, and then the add unit is pumping data to the multiply unit, and then the multiply unit is pumping data to the store unit, and then it gets out into memory.
But isn't systolic architectures considered MISD?
So that's a tough one, right? MISD is multiple instructions, single data. Well, you could kind of think of it this way also, right? In this case, you have so multiple instruction, single data is very hard to think of, in my opinion. That's why I said MISD question mark, right, for the systolic array in the lectures. Yes?
Systolic arrays don't usually talk about vectors.
That's right. Yes, exactly.
Code doesn't look like that.
Exactly, yes. That's the difference. That's why it's specialized, right? A systolic array is very specialized architecture.
But you do work on vectors.
You can work on vectors, that's right, but you don't necessarily have to. Basically, it could be any input. That's right. That's right. So but your code doesn't look like this, as he said. You're right. It could be vectors, but you don't necessarily have vector registers, for example. One of the major differences actually is the existence of registers, for example, vector registers that are global across all of the elements. In a vector processor or an array processor, you have these vector registers that are visible across all processing elements. Whereas if you think of the systolic array, go back to the paper you read, there's no such thing, right? It's really, you have this local piece of memory, and you operate on it, and then you move on to the next one. And then you move on to the next one. That's the difference. So the programming model is definitely very different. Yes? Sure, yeah, you should write some code, right?
It's not programmable, right? It's just specific for that application. You send it data, it does the work for you, and you what
So-
kind of code do you
So that's the most specialized case. You're right. In the most specialized case, everything is fixed function. And we've discussed that, and the paper discusses that, right, for convolution, for example. You can have a systolic array that just does convolution. But people figured out that it's very costly to design something like that. And also people saw that, oh, you can actually have a little bit of programmability in each of these little boxes that form the systolic array. One programmability could be the weights, for example, that you multiply with. Now you're becoming more programmable or configurable, right? You can, instead, while passing the data, you also pass which weights should you operate with.
But essentially, you're only pumping in data. You're not really pumping in instructions. You're tuning it.
That's right.
Putting in data.
That's right. So there's a spectrum between specialized and programmable. And people have started making systolic arrays more programmable over time. And you could think of that little execution unit as actually, let me try to open up that one. It's somewhere here. Actually, we were there, right? Systolic. Not this one. I didn't want this one. Did I want this one? It's easier to do this one. I think actually we've covered it twice. This is just to show you part 2, data flow part 2 systolic arrays. OK, there you go. This is what I wanted. There you go, more programmability, yeah. Yeah, if you look at this, this is very non-programmable, right? What we've discussed in class. You basically pump in the weights, pump in the, I guess, input data elements. And all this does then add and multiply, depending on the element. But each processing element in a systolic array now can store multiple weights, right? That can be selected dynamically on the fly, which means that you actually not only pump in the data, but you also pump in something that's programmed by someone that says, oh, you should use this weight for this data, right? So people have strived for this so that they can implement things like more adaptive filtering. Based on what's going on in the data, you do filtering better. Right? So you could actually think of more programmability. You could say that if the data coming in is greater than this, pick this weight or pick this weight. Now you're actually doing comparisons, right? So people built engines that started looking more programmable that way. The upside, of course, of that is now you're more programmable. You can execute more applications like this instead of just doing convolution. The downside is becoming more complex and less elegant. Right? Well, I shouldn't say less elegant. It's just more complex. Make sense? So systolic arrays actually subsume all of those, very specialized to very programmable. And I think actually I take them further. I take each processing element can actually have its own data and instruction memory. Now it's becoming more like processors, right? And data memory can store partial temporary results and constants. And this leads to the stream processing or pipeline parallelism ideas that we've discussed earlier, right? You get some data, you operate a kernel on one of the systolic array elements, and you pass the intermediate results to the next kernel that operates on the next element. You pass the intermediate results to the next kernel. And that's very much similar to what people call stream processing or pipeline parallelism. And this was one example of pipeline parallelism. This is also from the lectures. That's why I like these lectures on execution models, because it kind of stretches your mind, right? You start with a very specialized engine, and you start making it more programmable. And it starts looking like almost a multi-core strung together with queues in between it.
So was it
Yes.
envisioned that these systolic architectures would be implemented in FPGAs maybe, or?
Mm-hmm. No. Initially, when this was actually developed at CMU the first time, H.T. Kong was here at that time. And initially, they were implemented just for image processing. Convolution is one good example, for example, filtering of images. And that was the goal. They implemented, actually, let's see. Yeah, actually, I have these slides. Did I say this? Yeah, this was how it was implemented. It was a linear array of 10 cells. Each cell had a 10 megaflop programmable processor. Basically, it was programmable when it was implemented. It looked basically like this. You could think of it like a GPU at that time. Right? It's really, you have this host processor, and it basically interfaces to this. And this processor array actually does image processing. And it's fixed. Well, programmable processor arrays, but the structure is fixed. It's not an FPGA, right? But I think the concept itself led to a lot of other things like, well, this is again pipeline parallelism, right? Maybe it's a specialized form of pipeline parallelism. It's an accelerator. Does that make sense? Well, I guess it's not completely programmable, but it's somewhat programmable. This is what each element looked like. And I'd encourage you to read this paper. We get back to a question that you asked, actually. How does it differ from systolic arrays? But I'd encourage you to read this paper, The Warp Architecture and Implementation, if you'd like to see more details. I don't know if a warp computer exists here on campus today, but it's been a while also. Almost 30 years. Yes?
So the different topic in terms of data flow, you mentioned something about synchronization. But I got confused because if it's pure data flow, immutable state, what do you need to synchronize everything?
If it's pure data flow with immutable state, you said? That's right. Well, synchronization, let's see. Synchronization maybe at a higher level could be difficult, right?
Yes, what would be an example that actually
So if you actually have a transaction, for example, how would you implement in data flow?
But why do you need a transaction if there's no immutable state? Everything is just a function.
Oh, I see. If everything is immutable, you're saying. Yeah, so I think this goes back to the philosophical question of you may want some mutable state. Right? Yeah, then synchronization becomes difficult. So if you think of a database, for example, it's very hard to implement a database with no mutable state. Right? Say it again? That's right. So I think that's a very different way of thinking about a database from a traditional way. So if you actually can implement everything with no mutable state, basically whenever you write to something, you have a new copy, right? Basically, you don't write to the same thing twice. Then data flow is beautiful, right? You can implement synchronization. But there are some constructs that people have argued over time that it's very difficult to do this. Database is one example, right? Because what you have is some shared data, and you're actually operating on it, and you want to have you want to merge multiple updates to it. Right? Then the question is, how do you do that without any immutable state? That's the reason why that comment was there. Synchronization is difficult.
So how do you do it?
Yeah, how do you do it? Basically, somehow you need to implement locks in data flow, right? At that high level. And that may be difficult also. So I don't have the answers, actually. People have looked at the answers. But if you look at this, let's go back. This brought people to models that are more coarser-grained data flow. And the idea is you don't execute each individual instruction as data flow, but you execute threads in a data flow manner. Right? Now your thread can be a critical section. Right? You can say, I'm going to launch this critical section if its inputs are ready. And the critical section executes atomically, right, once its inputs are ready. So everything else is data flow, but this part of the code, that's the critical section, once it starts executing with all of its inputs once it fires, if you will, it looks like a big node. And it just finishes execution, and then after that it generates its tokens. Does that make sense? That's actually, these are actually interesting models. People went into these models exactly because of these problems. One of the problems was how do you support synchronization? Let me get back to this. I'll show you a pictorial example of it. Let's see, where is this? And I'll someday figure out how this PowerPoint is designed. Yeah, data flow part 2. It has to be here. So we were at the right place. Okay, macro. This is called macro data flow. Yeah. Okay. Yeah, I mean, there were many reasons what drove people to this. getting rid of the pure instruction-based data flow model. And there were two models to actually fix the problem. One is keep control flow at the ISA level and do data flow underneath, preserving sequential semantic. And this is the model we've been used to for a long time, right? Out-of-order execution, restricted data flow. So you all know this. But the second model that didn't succeed, or that wasn't explored to enough detail because this model was so successful, was keep the data flow model, but incorporate control flow at the ISA level to improve efficiency, exploit locality, ease resource management, ease synchronization, all of those reasons. And the basic idea is this, what I told you. Incorporate threads into data flow. Threads are statically ordered instructions. When the first instruction is fired, the remaining instructions execute without interruption. And it looks kind of like this, basically. Now you have these strongly connected components that are your bigger data flow nodes, if you will. And your processor needs to be able to execute these different instructions or collection of instructions at the same time. And you could think of this as a thread within a data flow, right? It fires when its inputs are ready. It gets executed. And once it's done, well, it's atomic, basically. Once it's done, you actually send the tokens out of that block. And if you read this paper, this is actually a good paper. I didn't assign it because you already have too many papers to review. This was written toward the end of the time where data flow, well, this is actually while Intel was building the Pentium Pro machine, right? Around that time, Intel was starting the building of the Pentium Pro machine. And after the Model 1 papers were published, and that was done in 1984. Data flow was very popular in the 70s and early 80s. And people figured out all of these problems that I discussed in the lecture, right? All of the advantages and disadvantages. And they've developed Model 1, and they've also started developing Model 2. And this paper is an example of that Model 2. It's a bit late. It's 1989, as you can see. But that basically talks about this concept. And I guess you can read that, right? Yeah, easier to implement serialization and critical sections, for example, is one of the advantages. But there are other advantages also. Like now depend or independent instructions can execute back to back, right? You don't need to generate tokens for that, right? You know within this code, this instruction will enable that instruction. They can just execute back to back in a pipeline fashion. You don't need to go through all of that token matching logic. So that improves efficiency of a data flow processor significantly. And you can have registers, right, within that strongly connected components. Your programming model is not only data flow, but also data flow plus control flow. So the registers is great for reducing the communication delay. Right? If you can put something in a register and get it back in a register within this small block, then you win significantly in terms of the communication delay. You don't need to broadcast it all the way to the matching logic, which consumes a lot of power. Yeah, and also it reduces less overhead, right? There's no need for token matching within this block because it's a thread, essentially, small thread. And no need for token circulation, again, within the block. So this got rid of a lot of the issues related to data flow. It's while still keeping the data flow at the programming model level. And obviously, it eased the serialization. And you can read this paper. I would actually definitely recommend this paper if you're interested in this. They have a good treatment of the problem. Well, why didn't it succeed? Well, maybe firstly, it was a bit late. The second is it's still changing the programming model, right? It's not single thread execution. It's not von Neumann. The higher level programming model is still data flow. And you have still a little von Neumann component inside it, right? This is kind of the von Neumann component, if you will. So it's the other way around. I think this is still very interesting to explore going forward with larger scale machines that we have. Actually, you could argue higher level programming models look like this. Not the implementations, but you have threads communicating with each other. At the higher level, threads get generated based on the data flow on different machines, right? If you're programming a cluster, for example, this could be a good model of programming at the higher level. But maybe machine design going forward, too. So I would definitely recommend this paper. It's This is one of the chips that was built in Japan. There were many chips actually that were built all over the world in data flow, but this is trying to get rid of a lot of the overheads associated with instruction-based data flow. Okay, what else?
So how are interrupts handled at all with these storage?
So that's the tough part, right? That's one of the killers of data flow almost. Well, actually, no, I shouldn't say interrupts. Interrupts could be handled, right? It's really the exceptions, right? It's really when you really need precise state for something. That is very difficult, right? Actually, here. So in 447, actually, we didn't cover it in 740, but in 447, I can make a distinction between interrupts and exceptions. Interrupts are actually external to the process that's running, and they're handled within the system-level context. Exceptions are internal to the process, and that you usually need to handle an exception right away to proceed. So page fault is an exception, for example. Null pointer dereference could be an exception, right? It could be a general protection exception, for example, in x86. Access violation exception. These are internal to the process. Interrupts are external. I think interrupts are a little bit easier to handle in data flow as long as you don't need precise state. But exceptions are difficult to handle. Let's say you get a null pointer dereference and you want to debug your program, right? You really need precise state at that point. So this should have been phrased as no precise state and debugging difficult. Well, I guess it is phrased that way, but maybe I should remove the interrupt from here. So I guess let me handle the interrupt first. I guess it really depends on the interrupt, but if you get the interrupt from a device in data flow, it's really easy actually, because now that interrupt generates a token that fires that is matched by a block that's waiting for it. And the block that's waiting for it is probably a system level handler, right? That's the resource manager. It's part of the data flow graph that your resource management is. And that part gets fired based on that interrupt. So handling that is easy. Debugging is really hard. Figuring out where you are in the precise state is really hard. And I assume that's what you were asking, really. Because it's very hard to know what's even a precise state, right? Because you have this graph, and some things are executed, and the execution order depends on the latencies in the system. Unless you have the exact same execution order with the exact same latencies, the next time you run the program, it's very difficult to get to the same precise state, right? Because you don't even have that precise state, right? In von Neumann model, precise state is really easily defined based on the semantics. At that point in time, one instruction, there is a state where all previous instructions are executed and nothing after that is executed. In data flow, you don't have that. All you have is a graph, right? And that problem has not been solved, really, with data flow.
So you just can't do anything?
It's very difficult to debug, yes.
I mean, what happens in a page fault?
What happens in a page fault? Well, what could happen in a page fault is certainly you can. Page fault may not necessarily require precise state, right? So there are cases where some exceptions require precise states, and there are some cases where some exceptions may not require precise state. Where you really, really, really need debugging, where you really, really need precise exceptions is really when you're debugging. You want to be able to say, I was at the state, and I'm going at the state again. With page faults, I can imagine mechanisms. When you get a page fault, you, again, fire up another part of the resource manager data flow graph. And that handles the page fault while this process is waiting. So imagine everything as a huge data flow graph, including the system code and the user code. And they're connected with some arcs. So with page fault, you can handle that way. You don't really need that precise state, because you design the entire system to be that nicely working data flow graph.
So you can handle the page fault as an interrupt.
Say it again?
You can handle the page fault like an interrupt.
Like an interrupt, exactly. You fire up some system level code that handles that exception. Say it again. Logs meaning? Yeah, it's very difficult. It's really difficult to get to the same state again. That's the problem. With debugging, you really want to get to the same state again. It's actually a very a harder problem than the problem that happens with multiprocessor debugging, right? When you execute a multi-threaded program, you really want to replicate the exact same state. So there are these bugs that happen in multi-threaded programs that only sometimes happen, occasionally happen. Why? Because things have executed in some order that exercise the race condition that exercise the bug, right? Because you may have forgotten a lock somewhere. It doesn't always lead to a bug, right? Because of the reasons that we've discussed, right? Maybe the threads actually, that was actually one of your questions, right? Maybe threads execute, threads do not need the lock at the same time. Then you get the correct answer, right? But that bug is hard to reproduce in the next run because there's nothing that dictates the same order today. People are working on this to ensure that there's deterministic execution across multiple executions of multiple executions of the same processor, same multi-threaded program. But we don't have that today. And it's the same problem, except it's not only in those cases where you synchronize, it's in all cases, right? The entire system is a data flow graph, and you never know where you are in that data flow graph. One time you execute, it gives you some answer, there's a bug. The next time you execute, it's very, very difficult to replicate it. With multi-threaded applications today, at least you can think of potentially replicating it. With this one, you can forget about it, perhaps, unless you're running a very small program. Okay? These are good questions. And that's one of the big reasons why this model has been unsuccessful. That's why this is at the top, right? That's the most important reason. Data flow, most important disadvantage of data flow. And I actually tried to order it based on importance. The second one is really this dynamic data structures. The other ones potentially can be solved. Actually, instruction cycle is inefficient, for example. There's delay between dependent instructions because you need to go through this matching store. But that could be solvable, as we've discussed.
Is there any concept of barriers here?
So there's that was one of the instructions that I didn't talk about, but I kind of flashed in one of the slides, right? You could actually have an instruction that has barrier synchronization, right? Basically, it takes in lots of tokens, and it allows all of the tokens to proceed once all of the tokens arrive. Actually. Oh, it's not here? Oh, no, this is the second lecture, yes. Let's go back to part 1 probably, right? Or is this SIMD? It is SIMD. So multi-threading is today. Do I not have that? Oh, there you go. Yeah. You could have a node that looks like this. Right? Now you could implement this in hardware. It's a little bit more overhead, obviously, because you need to match a lot of tokens, but you could do it. What else? I guess let's go back to what we've covered. Jog your memory. I guess we have talked about pretty much all the models that we've covered. You had questions. Like SIMD and GPUs we've talked about. So going forward, making GPUs execute general purpose applications is definitely an important research direction. And we've covered briefly dynamic warp formation. Do you remember what that is? That's actually one of the earlier works. People have developed that. You cannot do something like that in SIMD. for example, because SIMD is very hard-coded. But with GPUs, what you can do is a warp is essentially a collection of threads that execute the same, that are at the same program counter, right? They're executing the same program counter. These threads do not need to be the same threads they were the last time. The warp doesn't need to contain the same threads all the time, right? Let's say you have a branch. Because you have threads now, you can have branches. Some threads go this way, some threads go the other way. Now, you form a warp. If you actually create two warps out of this, you will create two warps because you have to execute both. Both warps will be underutilized, right? Because, actually, let me pull up the slides over here. And I'll hopefully be able to find it this time. There you go. In fact, it was faster. Yeah. Yeah, I guess you've seen the branch divergence, so I'm going to skip that. But let's say you had some number of warps over here that diverged for some reason. You have two warps that happen to be executing at the same PC, same program counter. You can simply merge them, right? If you know that this warp has 1, 2, 3, 4 threads that are executing at program counter A, and this other warp has 3 threads that are executing at program counter A, you can just merge them. Does that make sense? Because they are really threads, right? They have their own state. With SIMD, it's very difficult to do this. Then you can do this also. So this is part of the lecture, so you should really take a look at them. Right? How many of you have watched this lecture? OK, most of you. And the others who haven't watched, you're late. OK, well, you can actually see, I'll go through this just to give you the key idea. There are issues related to this, and people have worked on this afterwards, and we've worked on it too. But this is one thing that can make GPUs much more general purpose than SIMD. Why? Because you get to, all of the threads are executing this code, right? Remember, each of this is a thread, and they're executing the same program counter. When they get to a branch, you form two warps, right? One of them goes through path A, and you have another set of warps, let's say, that go through path A also. Now you can merge them, right? Because you have many, many threads executing the same code over and over. And that's the idea. And at the end of the merger, you have one warp that's populated a lot, and another that's not populated. Right? And then if you have many, many warps like this, you can keep merging them and get much better utilization. Why is it bad to have a warp that looks like this? Basically, that has 2 threads only, 2 active threads only. Utilization, right? Because, well, in this case, 1, 2, 3, 4, 5, 6, 7. Is it 8? Yeah. Let's say you have 8 wide SIMD, 8 execution units. If you have a warp that looks like this, that has only 2 threads, you're utilizing only 2 of the execution units out of the 8. You really would like to fully utilize. And this paper talks about it. And I'm not going to go over this because it's in the lecture. And you can certainly play the slides yourself. So you could do this with this kind of execution model. Single instruction, multiple thread. You cannot do it with SIMD. OK, what else? Let me go back to here. Yeah, we've covered other models also, VLIW and decoupled access execute. Any questions on that? That was last Friday. No?
What's the difference between VLIW and superscalar?
No.
Just that VLIW can execute everything parallel.
No, superscalar is like that too. So the commonality is multiple instructions are fetched, decoded, executed concurrently. in the same time. You don't fetch 1 instruction per cycle. You fetch 4 instructions per cycle. The main difference is who does the job. Right? Is it the hardware or the compiler? In VLIW, it's the compiler that packs together independent instructions in a very long instruction word and ensure that they're independent. In superscalar, it's really the hardware that actually nobody packs instructions for hardware. The hardware fetches 4 instructions, let's say if it's 4 byte superscalar, and it figures out which instructions are dependent, which instructions are independent, and keeps executing based on those dependencies. As a result, superscalar is more complex because you need to have a dependency check logic between instructions that are concurrently fetched. Right? Whereas VLIW is much more beautiful at some level, right? Because the compiler packs these instructions that are independent, and the hardware doesn't need to do much. The hardware knows that the instructions that are fetched concurrently within this bundle, within this VLI, a very long instruction word, are independent. So hardware can simply execute them. Right. There's no need for dependency checking. And the compiler also knows the machine structure in VLIW. For example, if you don't have symmetric execution units, you have load unit here, add unit here, multiply unit here, the compiler can put the right instructions at the right lanes, if you will, such that they directly go into the execution units. Whereas with superscalar, you don't have that luxury. The compiler doesn't do much, doesn't do anything. Let's say that's the assumption. You fetch 4 instructions, and the instruction that you fetch load maybe at the beginning, if you look at the machine structure, to the left of your machine, but the load unit may be to the right. Now you need to have a crossbar to actually route these instructions within the machine. So you get rid of that logic too with VLIW. The downside, of course this comes at a downside, right? How do you actually find instructions that are independent to put together with VLIW? That has been a difficult problem with many VLIW engines. And actually, we have not covered it yet, but you'll see that when we cover static instruction scheduling, you'll see many methods for designing compilers that try to find multiple instructions that can be executed in parallel. It's very difficult to find multiple independent instructions that can be executed in parallel within a single block, single basic block. So many compilers today use concepts like superblock execution. That's your required reading. It will be your required reading for this lecture. Yeah, the superblock paper. Many compilers, well, we've covered this in 447 too. If you've taken 447, you remember this hopefully, right? Yes, some of you do. Basically, many compilers profile the code and generate a larger block that is frequently executed and try to schedule instructions within that larger block. And this larger block, larger scope, enables the opportunity to find more independent instructions. And the assumption is that this block is frequently executed. The code should be optimized for this frequently executed path. And if the code actually deviates from this path, you have some penalty to pay, which is a fix-up code. Right? And we will get to this on the 22nd. So it's OK if you don't know this yet. But if you've taken 447, you should really know this. OK. Does that answer your question? What else? Look, you guys asked some good questions. Keep it coming. We still have some time. Or we can end up early. Yes?
Going back to some hybrid memory lecture.
Hybrid memory. OK, that's a long time back.
When you use DCM and DRAM, you really need row buffers?
when you use PCM and NVRAM, do you really need row buffers? Well, you do need something to do the reading. But maybe you don't need row buffers that are as large.
Right.
Right.
You have to buffer it before
That's it.
sending it to the line.
Actually, you don't, in the strict sense, you don't really need it, right? Because everything is non-volatile. You just need something to sense it and then send it. So you don't really need them. You're right.
But all
But-
the designs are talking about row buffer locality and placing them either in PCM or in
But practically, it's a good idea to have them. Why? Because it takes such a long time to access the array. If you have some sort of locality, you really would like to exploit that on chip. That's the main reason. And that's the benefit of a row buffer. Because you still need to design your array or subarrays in some rectangular shape, which means that you need to enable a row, because that's done to minimize the latency, right? Minimize the interconnect latency. Now, once you have that structure, it just makes sense to, because you're enabling an entire word line at the same time, it just makes sense to buffer a good chunk of it at least, in anticipation of locality, basically spatial locality. If you don't have any locality, then maybe you're right. If there's no locality, it may not make sense to have a row buffer.
But in DRAM, it has more function than this locality.
Absolutely, yes. In DRAM,
Back.
exactly. In DRAM, a read of the row is destructive. That activate is destructive. So you have to buffer the entire row. Otherwise, you'll lose data.
So they're assuming that row buffer, even in PCM, would be faster than accessing PCM itself.
That's right, yes. That's right. Because that also makes sense, because once you read the entire array, you better latch it somewhere that's faster. Right? But that's a good thought, actually. It's good to rethink some of these emerging memories based on their characteristics. And that's exactly the reason why row buffers can be smaller. Remember the architecting phase change memory paper? Architecting phase change memory is a scalable DRAM alternative paper in ISCA 2009. We experimented with different size row buffers. We could do that because the reads are not destructive from a row. What else? You could ask questions from other lectures too, as Purti did. And I guess I can give you an overview of what's coming next. Well, who watched the multi-threading lecture for today? No one? OK. So this week we're going to cover, actually pretty much the rest of this week, we're going to cover multi-threading. It's another fun topic. This is hardware-based multi-threading. How do you support multiple hardware contexts, multiple contexts in hardware? And it's a lot of fun. People have looked at this a lot. We're going to cover different forms of it. You're already familiar with some of them. Definitely fine-grained multi-threading. If you've taken 447, you've seen multiple questions on it. But we're going to look at that. And we're going to look at more coarser-grained multi-threading, like switch-on-event multi-threading. When you get a cache miss, maybe you switch to another thread, right? The question is, how do you do that? So it incurs a lot of overhead. But there have been machines that have implemented switch-on-event multi-threading. And you'll see some of them. And then we'll talk about simultaneous multi-threading also. And the difference in simultaneous multi-threading is basically you can now execute instructions from different threads in the same cycle. You can just dispatch those instructions in the same cycle. In fine-grained multi-threading, you basically do cycle by cycle. This is also called cycle by cycle. Coarse-grained multi-threading, it's really at the granularity of events, you go to a different thread. Whereas at simultaneous multi-threading, it's truly simultaneous. You can do scheduling of instructions from different threads concurrently in the same cycle. So this should be fun. We're going to cover a lot of aspects of it, like throughput, fairness, quality of service.
And people have tried to develop solutions to and this is with a multi-threaded core, different threads actually share the core, right? If one thread stalls, you don't want to hog all of the other threads. But this problem has been present. If one thread actually does a load, gets a cache miss, it can stall the other threads. How do you handle this? Will be one of the questions that we will tackle. So it should be interesting. And this is actually a good research area too, going forward. How do you actually orchestrate the execution of many threads? Today, if you look at multi-threaded engines, you don't have threads per core that's greater than 8, I think. Is that correct? I think some of the Oracle machines are 8 threads per core. But Intel machines are 4 threads, or maybe 2 threads. Oh, is it 2 right now? OK. 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 And Niagara is 8 at this point. Well, Niagara was 8. I don't know what the latest processor is. Yeah. Yeah, you don't know. OK, maybe you can look it up. There's an Oracle T4 design, right? UltraSpark T4 design. Or is it T5? I don't follow it that closely. But yeah, basically that's the idea. If you have, but there are so many thread contexts, and adding more thread context actually costs a lot of hardware. One key question is how do you actually can execute many threads within a small number of contexts? I think that's a good problem to look into. Looking into basically taking a fresh look at multi-threading today with many threads present is definitely a good research topic. Maybe some of you can pick it up. And after that, we'll go into out-of-order execution. So out-of-order execution lectures are actually from 447. But I intend to, I assign some readings over here. And static instruction scheduling is also from 447. So if you've taken 447, you'll just need to read the material and just brush up better. But we're going to go deeper by reading the papers and having the discussion. That's the interesting thing about 740. Not everyone who's taking 740 has taken 447. Yes?
I have a question about today's assigned reading of our pipeline shared resources.
Let me see, which one? Oh, today's assigned reading.
I kind of didn't get it significant.
Oh, I see. I'm not going to give you because this is a review reading, but I can tell. Why is it significant? Well, it's actually a short paper, right? 1, 2, 3. Yeah, it may be hard to understand actually initially, but this is the first paper that actually talked about fine-grained multi-threading. This is by Burton Smith. I shouldn't say first paper, but the first understandable paper that talked about multi-threading. There's a first paper that could be easier to understand for you, I should say. There's a CDC 6600 paper by Jim Thornton that introduced multi-threading within the I/O unit of the CDC 6600. But the terminology of that paper is very different. Maybe the terminology of this paper is different enough that you're asking this question. But basically, this will become more clear when you watch the multi-threading lectures. I cover this paper a little bit. But this is the first paper. This is a paper that introduced fine-grained multi-threading as it's implemented in the Denelcore HEP machine, heterogeneous element processor. That's why I assigned it.
Okay, I got thrown off by the Mindy paper. It's heading high.
Where?
No, I mean, it's labeled Mindy computer, so I thought it was actually a multiple.
Oh, no. It's a MIMD computer. This is what you're asking?
Yeah, so I thought it was talking about
Multiple instruction, multiple data. Yes.
but it's actually talking about multi-threading.
Exactly. So multi-threading and multi-core are both examples of the MIMD model, right? Yeah, multiple instructions, multiple data. It's not multi-core. Yeah. It's a very interesting processor, though. You'll see it in the lectures, lecture of today, actually, the multi-threading lecture.
It basically had a large number of threads. Let me actually pull it up briefly. This paper actually talks about a lot of concepts. It talks about how multi-threading is done. It also talks about how synchronization is done, full empty bits. We've covered full empty bits several times, right? Multiscalar, remember, had full empty bits in its register file. When a register is available, the bit becomes full. When a register is not available, it becomes empty. This is a machine that did full empty bits in its entire memory. Each memory location had a full bit or an empty bit. And when a thread wrote to that location, it made the location full. And this is how you could synchronize between different threads. And there, I don't remember if it's in this paper. I think it's in this paper. There's a code example that uses full empty bits. There you go, in Fortran. You could take a look. It takes a while to understand. Even though it's a 3-page paper, it has a lot of meat in it. So you can see how full empty bits are used to do synchronization. OK? Should be fun to read this paper, I think. Yeah, you can see that there are Fortran extensions that they did to incorporate parallelism, incorporate the full empty bits. And you'll need to get used to the syntax a little bit. But this is actually this is the other reason why I assigned this paper, so that you can get a sense of the full empty bits. This paper talks about the general architecture very quickly in 3 pages. The other thing that this paper talks about is the switch. And I'll have to look at it. But yeah, this machine, the Denalcor HEP machine, this was Burton Smith, who's done a lot of work in multi-threading. He was a professor at University of Colorado at that time. And then he formed this company called Denalcor and designed this heterogeneous element processor, which incorporated a lot of these interesting concepts in it. And one of the concepts was this is the interconnect of the machine. And the interconnect actually employed deflection routing, which we've also talked about earlier. And he talks about it over here a little bit. Right? Yeah, for example, if conflict for a port occurs, the node routes one of the contending messages correctly and the rest incorrectly, meaning to a destination that the message doesn't want to go to help ensure fairness, as an incorrectly routed message has its priority incremented as it passes through the node, and preference is given in conflict situations to the messages with the highest priority. That's simple heuristic. It doesn't necessarily provide live lock freedom, though, like which we've covered that, right, in previous lectures, in earlier lectures. So this puts together a lot of different concepts in a machine. And later, these concepts actually went into some of the supercomputers. Burton Smith went to Terra Computer Company, which designed massively multi-threaded machines, which were based on some of these concepts. And Terra later got bought by Cray. And a lot of the Cray machines got influenced by a lot of these concepts. And you'll see the progression also in the slides. But that gives you historical context of this paper, hopefully.
So it introduced multi-threading.
So no, that's too far-fetched, probably. It's basically, I would say it's reintroduced fine-grained multi-threading into computer architecture.
It talks about shared resource management and communication. It doesn't really talk about,
Multi-threading that much?
yeah,
Yeah, it's really this part. It's really this early part. It doesn't analyze it that much. You're right.
it just says if time multiplexes, then it doesn't really explicitly even say multi-threading.
I guess that's true. You'll need to. Otherwise, I need to assign you the HEP heterogeneous element processor technical documents, which I cannot even find. So the machine itself actually had the multi-threading hardware. So this is very similar to how Niagara was built, actually. So Niagara has very similar multi-threading mechanisms, fine-grained multi-threading mechanisms. But yes, you're right. This paper per se doesn't focus on the multi-threading aspects of the machine. It's more of a machine overview, as the title suggests, right? Actually, if you're interested, maybe we should change this paper and assign you a longer paper. And I'll show you that paper also. Actually, I won't do that assignment at this point, but I think if you want to learn more, yeah, you should take a look at this paper. this goes into a little bit more detail. And maybe I should have assigned this paper. This is written a little bit later. I believe it was written in 1981 instead of 1978. But it's the architecture and applications of the HEP multiprocessor computer system. And it goes into a little bit more detail as to how each of the components operates. Yeah, I don't know if it has a code example. Yeah, it does have it. Should we switch to this paper? No. OK, good. But let's put this up. I'm not sure if it's part of the required readings, but not review readings. So you'll get more information from here. I encourage you to look at this. And I don't think you'll still get a whole lot of detail, because this is still an overview paper of a machine. But the machine itself actually did fine-grained multi-threading. Yes?
In this paper, it talks about the MIMD computer having two queues, one for the program memory and one for the data memory. So is it similar to the idea of DAE?
So at some level it is, but not really. Those are actually queues where the threads are waiting. Threads wait for either the instruction memory or data memory. It's basically to manage the resources. It's not to decouple the execution. Basically, a thread needs to fetch an instruction, decode an instruction, and then execute an instruction. And it can go to data memory at that time. A thread cannot be present in two queues, basically. That's the difference. In DAE, you have a single thread that's divided into an access processor and an execute processor. Here, you have many, many threads. And a thread can be present in different queues at any given point in time. If it's an instruction memory queue, it's just waiting for that, waiting to fetch that instruction. If it's in the data memory queue, it's waiting to fetch the data for an instruction. Okay? So it's very different. In this case, the queue is really for the resource management. Whereas in DAE, if you remember, there are queues over there also, but that's for communication between the access processor and the execute processor to ensure that they synchronize properly within the instructions, right? Within the same instruction stream, same thread. OK. OK. I guess what else? We have 10 more minutes. Are we?
Question about the GPU overview paper. It went into a lot of detail about the visualization pipeline, and I just didn't get it.
Yeah, that's sure. That's not the focus of this course. So if you didn't get it, that's fine. I can recommend you some papers offline. That's really the GPU graphics part of the GPU itself. I didn't necessarily want to focus on that in the course itself. So if you didn't understand it, that's OK. But if you're interested in understanding it, then I can point you to some papers. So that shows that's actually another example of how a very specific processor becomes much more general purpose today, right? It has all these fixed function units that became programmable over time. But there are still some fixed function units that need to be there for the graphics processing purpose, very specialized for graphics. What else? I guess I can overview some of the papers that are coming up too. So it should be exciting. Where is this? Not that one. Is it this one? Yes. Yeah, these are today. The other paper is an SMT paper. It's not the earliest SMT paper, but it's a more comprehensive simultaneous multi-threading paper, INISCA 1996. There are a bunch of other good papers over here too, so you can read them. Yeah, and this is due, is this Friday? Yeah. So on Friday you have two more papers. One is on the use of multi-threading hardware to accelerate a single-threaded program, helper threads. We've discussed that in various contexts before, but it's good for you to read a paper that introduced the concept. And the second one is on thread scheduling on a simultaneous multi-threading engine. Which threads do you pick to schedule together on an SMT machine? Because the threads tightly share resources, right? And the idea over here is pick the threads that go nicely with each other, symbiotic threads, if you will. And you can read the paper to figure out. But this is the paper that introduced the weighted speed-up metric that you've come to know and love probably by now while you're reading the papers, right? So you can see why they introduced that weighted speed-up metric as well. And actually, there will be some lectures where we talk about fault tolerance too, because one of the topics that we'll cover is what else can we do with multi-threading hardware? Now that we have this hardware that has multiple hardware contexts, we can run multiple different threads in it, sure. We can run multiple different threads from different applications also, or the same application. But what else can we do? And one of the things that we can do is to use the same hardware for fault tolerance with some additional mechanisms. And the basic idea is to do redundant execution. You can run the same thread at the same time in different contexts and compare the results. Right? If one thread gets a fault for some reason, maybe because of a fault error, because of a soft error, a transient fault that hits part of the machine, the hope is that the other thread that's executing the same instruction doesn't get that fault, and you detect that something went wrong. And you can do transient fault detection. So these three papers talk about that over here. Okay, and after that we'll go into out of order execution. And you have this reading, a long reading that's relatively old, but it's still a good overview. The microarchitecture of superscalar processors, which should really be titled The Microarchitecture of Superscalar and Out of Order Processors. That talks about how the superscalar out of order processors are designed. That should be good, hopefully. Okay. Anything else? Anything burning in the last 4 minutes? Yes. Oh, lectures on that? That's no lectures, but you can certainly go to office hours to meet Hongi, or you can talk to me. But that's, while I think that's a good research area that relates to computer architecture. A lot of things actually relate to computer architecture. We won't have lecture material because we already have more than enough to cover in the base material. Okay? Okay, I guess I'll see you next time.